Good afternoon, students. I hope you are healthy and fine. So now we are going to begin the lecture where I have left. If you remember, I had discussed in the last class about the armature controlled DC servo motor, and the basic aim was to introduce you to the concept of how we can use the mathematical modeling to design any control system components. Right. So now we are going in this series. Now we are going to see the next component. That next component is nothing but a field controlled DC servo motor. Now, if you have understood the concept of an armature controlled DC servo motor, then it could be quite easy to understand a field controlled DC servo motor. Now, as you can see, a field controlled DC servo motor, though I have not shown any diagram here, but a field controlled DC servo motor is a motor which is controlled from the field side and the armature side is kept constant. Now, what I mean by armature side constant? I mean to say that armature current, the supply which we are going to give to the armature side is kept such that the armature current is kept at a constant value. Right. Now let us see the mathematical equations which will govern the modeling of a field controlled DC servo motor. Now, from the basic principles, it is a well-known fact that the air gap flux in any DC motor is proportional to the field current, which is governed by the famous magnetic circuit rules, where it says that the flux is equal to magnetomotive force. As we know in an electric circuit, it is analogous to an electric circuit where I is equal to V by R. I is equal to V by R. So that is current is equal to voltage divided by resistance. Similarly, flux is equal to magnetomotive force divided by reluctance, magnetic reluctance. So magnetomotive force in any magnetic circuit is proportional to number of turns into current. So if number of turns in a winding are constant, so and if the reluctance of the magnetic circuit is also considered as a constant quantity, we all know that the reluctance of any magnetic circuit depends upon the length of the magnetic flux path. It depends upon the area of cross section. It depends upon the nature, the permeability of the material. And we know that in a DC machine, the winding which is responsible for the control, which is responsible for the production of flux, is the field winding, right? So field poles. So the field windings are bound on the field poles, and a constant amount of field current is fed to that field winding, which will produce the flux. So in a DC machine, the magnetic circuit that is responsible for the field for the production of field flux includes a field winding supplied through a field current. Since number of turns are constant, since the length of the magnetic flux path is constant, area of cross section is constant, the material does not change. Therefore, we can assume that flux is directly proportional to field current. So flux will be equal to some kf into if. Now, the second equation of a the second famous equation of a DC machine is the torque is a cross product of flux and armature current. Now, as I have already told you that armature current was kept constant, right? So, if armature current is kept constant and flux was equal to some constant Kf into If, therefore the torque, which was proportional to some Kf into If into Ia, in this equation, Kf is constant, your armature current is constant, so it is represented by a new constant capital Kt. So the torque is a direct function of field current. So torque is equal to some constant Kt into If. Remember, student, this equation is valid. Phi is equal to Kf into If only in the linear region of magnetic magnetization curve. We know that there is a linear relationship between flux and armature current until there is no saturation. When that this relation is a linear relationship and it happens before saturation. So, I can say that while I am developing the mathematical model of a field controlled DC servo motor, I am considering the what to say approximation that my saturation effect has been neglected. So when the saturation effect has been neglected, therefore there only will be a relationship between the flux and the field current. As you already know that whenever we are going to whenever we are going to implement the concept of mathematical modeling for any physical system, we neglect non-linearities. We normally neglect non-linearities, and our syllabus also includes linear time variant system. So let us neglect the effect of magnetic saturation. So considering this, we can say that the electromagnetic torque T of that DC machine now will be equal to some constant into field current. Why? Because the rest of the quantities are considered constant. And why they are constant? Because our motor was controlled from the field side, not from the armature side. So armature current was considered as a constant quantity. So converting this equation into Laplace domain, Tm of s will be equal to some constant kt into if of s. This equation converted to Laplace domain. I have taken my previous lecture in which I have explained you that the back EMF of any DC machine is equal to some constant k into phi into omega. K phi omega. Right. Now here you have to. I think this equation is a bit. It has to be seen once again because here they have considered it only proportional to speed omega, but it also depend upon flux. And if you are going to change the field current, obviously the back EMF may be affected. The back EMF may be affected from the flux. Let I will see it anyways. So leave it. Now we go from the field side. Applied voltage to the field winding, which is the voltage which we have applying to the field winding, applying the Kirchhoff's voltage law. This voltage has to overcome the drop in the field circuit. The drop in the field circuit include the drop in the resistance of the field winding and the drop in the field inductance. So mathematical equation says that EF is equal to IF into RF plus LF into DIF by dt. Converting this equation into Laplace, so EF of S is equal to IF of S RF plus SLF because the operator d by dt, if we neglect the initial condition, in Laplace domain becomes S. So L into dIF by dt in Laplace becomes S into LF into IF. So from this equation, if I take IF of S common, so it becomes RF plus SLF. So this is the equation for the field circuit. Now the electromechanical equation. The total torque developed by the machine has to overcome the inertial forces plus the frictional forces. Now we are considering the effect of inertia and the friction to be jumbled only at the rotor of the motor. That means the total, this J represents the total moment of inertia of the load as well as the rotor of the motor. Similarly, this B represents the total moment of inertia of the motor as well as that of the load. Again, converting it into Laplace, it becomes Tm of s is equal to Js plus b into omega of s. There is no need to explain why this j into s came because j into d omega by dt has been converted into Laplace domain. So it becomes j into s into omega of s. We have taken omega of s constant. So now let us develop the block diagram. So the block diagram says you apply a field voltage to the field winding. That field voltage to the field winding, and this is the equation which is responsible for the Kirchhoff's voltage law. That is, if we divide the voltage by the drop, we give the current. We get the current, that is the field current. So field current multiplied by the torque constant gives the torque. Torque multiplied by 1 by Gs plus B from the electromechanical equation gives the omega. And omega when multiplied by the constant gives the back EMF. So we can say that this is a block diagram of a field controlled DC servo motor. And let us come to the third category of an servo motor, which is known as an AC servo motor. Now, first, I will discuss what are the constructional features of an AC servo motor. Right. An AC servo motor consists of two sets of winding. Basically, it is a two-phase winding. It is a two-phase motor. One set of winding is known as the control winding, and the other set of windings is known as the reference winding. Both the two windings are placed at 90-degree geometrical angle. That means they are having a physical angle of 90-degree electrical with respect to them. And they are also to be fed from two electrical supplies which should be displaced at an angle of 90-degree with respect to time also. That means there is a space displacement of the two coils by an angle of 90-degree, as well as the supply which is fed to these two windings also having a time displacement of 90-degree. Now, why this winding is known as control winding? Because this is the winding which normally controls the motor. Now, my question may be, from where you are going to feed this winding? आप इस winding को supply कहाँ से देंगे? Obviously, going back to the basic philosophy of control system, I will just go back. And as you can see from the basic philosophy of control system, we know that a reference quantity subtracted from a feedback quantity gives the error signal, and this error signal is actually given to an error processor, and this error processor is producing the actuating quantity which is controlling the plant. Now I'm going to correlate this slide with our armature controlled AC servo motor. Now, as I have discussed, that in a closed loop control system, error is responsible for minimizing error. That means the error produces the actuating quantity which controls the error, which compensates the error. So obviously, this winding should be fed from a differential amplifier or something which is comparing or doing the task of differential. How can I explain it? Let us say I am going to implement a position control. What is the meaning of position control? I am going to control the position of a shaft. Let us say the theta of the shaft. So what I'll do is I will set a reference theta, that will be theta r. Now I am going to control the theta of my load. So what I am going to do is I am going to compare the reference position with the actual position, and difference of these two positions, the mechanical difference, it may be linear distance or it may be angular distance. So this difference should be this difference of position or difference of angle is a physical quantity. It has to be converted into something which could control. So what I do is I convert the difference of position or difference of angle into an electrical quantity. Now, which transducer is helpful for me to do so? Obviously, I will have two types of transducer. One is a potentiometric error detector, another is a synchro, which I am going to discuss after this slide. Okay, so right now you should remember that whether it may be a potentiometric error detector or it may be a synchro, both are meant to achieve the task, that is, they convert the difference of two positions into an equivalent electrical signal. So the electrical signal output of a synchro or of a potentiometer is proportional to the difference of the two positions. So this difference of the position which gets converted into a voltage with the help of our transducer, which may be a synchro or a potentiometer, is the voltage which is the actuating signal. So this actuating signal has to be applied to that part of the my servo motor which will make the motor to operate. So obviously in our case, since it is an AC servo motor which has two sets of winding, my question is, if you are getting an error voltage from a potentiometer or from a synchro, where are you going to apply that error voltage? Whether you are going to apply it to the reference winding or you are going to apply to the control winding. The answer is you are going to apply that error voltage to the control winding, because this is the winding which is going to make this motor to operate. So the error voltage coming from an error detector or a transducer is applied to the control winding. Now this is the operation of a AC servo motor. Let us go into the mathematical equations. We know that this is the speed torque characteristic of a normal induction motor, which has a negative slope in this region and a positive slope in this region. Now, I want a linear relationship between torque and speed. I want a linear relationship between torque and speed. Also, you very well know that from the basic concept of machine that this region of operation is considered as the stable region of operation. Remember, in any motor, when the slope between torque and speed is having a negative slope, when the slope is negative between torque and speed, then that region is considered to be a stable region because it has an inherent property to achieve stability. I will explain it in this way. Suppose you are operating at this point. At this point, let us say this is the torque and this is the speed. Suddenly, there is a sudden increase in the load torque. So, an increase in the load torque, I would rather explain it in Hindi, so it would be more easier. मैं ये बोलना चाहूँगा कि एक थ्री फेस इंडक्शन मोटर का ये जो रीजन होता है, जिस रीजन में आपकी टॉर्क स्पीड कैरेक्टरिस्टिक्स नेगेटिव होती है, उसको स्टेबल रीजन क्यों बोलते हैं? क्योंकि अगर आप इस रीजन में कहीं ऑपरेट करते हैं, सपोज करो आप इस पॉइंट पर ऑपरेटिंग पॉइंट है आपका, यहाँ ऑपरेट कर रहे हैं, इस पॉइंट पर आपकी स्पीड इतनी है और आपकी टॉर्क कितना था। सडनली अगर लोड बढ़ता है तो लोड के बढ़ने के साथ मोटर की स्पीड धीमी होती है। जब मोटर की स्पीड धीमी होगी तो आप इस एक्स एक्सिस में इस तरफ बढ़ेंगे, लेफ्ट हैंड साइड पर जाएंगे। जब आप लेफ्ट हैंड साइड पर जाएंगे तो आपको रिड्यूस्ड स्पीड पर आपको ज़्यादा टॉर्क मिलेगा, क्योंकि ये कर्व है, इसका नेचर ऐसा है कि जब आप दिस कर्व इज हैविंग ए नेगेटिव स्लोप, सो दैट मीन्स if you go towards this side, if your speed reduces, you get a higher torque. तो हुआ क्या था? What has happened? It was that motor was running at a stable operating point. Suddenly, there was an increase in the load torque. When there was an increase in the load torque, the speed of the motor has reduced. When the speed of the motor has reduced, it has resulted into a higher torque. So higher torque would have resulted into an increase in the speed. So obviously, automatically, the speed of the motor may have increased, and it has the reduction in the torque, which was due to the load, was being compensated by the characteristic of this induction motor, by this the slope of the slope of the characteristic curve, which has resulted into the fact that at a reduced speed you have obtained a larger torque, so there was an equilibrium again. यानी कि हिंदी में इसको मैं ऐसे समझाता हूँ कि मोटर के ऊपर सडन लोड बढ़ने की वजह से उसकी नेगेटिव स्लोप की कैरेक्टरिस्टिक्स की वजह से जब स्पीड कम हुई तो उस मोटर ने ज़्यादा टॉर्क पैदा किया, और जब ज़्यादा टॉर्क पैदा किया तो ऑटोमेटिकली टॉर्क का बैलेंस हो गया। क्यों? क्योंकि ये मोटर की स्पीड इसलिए कम हुई थी क्योंकि मोटर पर लोड बढ़ा था। अब उस लोड के बढ़ने की वजह से मोटर की स्पीड कम हुई, और स्पीड के कम होने से उसकी कैरेक्टरिस्टिक कर्व की वजह से उसने ज़्यादा टॉर्क मिला हमको, और ज़्यादा टॉर्क मिलने से वापस टॉर्क बैलेंस हो गया। तो इस तरह से ऑटोमेटिकली इक्विलिब्रियम कंडीशन मिल जाती है। तो आई कमिंग बैक टू अवर इंडक्शन मोटर, व्हाट आई मीन टू से इज, अगर हम इस रीजन में ऑपरेट करें किसी इंडक्शन मोटर के, तो वी विल गेट ए स्टेबल ऑपरेशन, बट इंडक्शन मोटर हैज this characteristics. So if I would be able to shift this curve towards this side, so I will get a negative slope. So what is it? It is nothing but shifting the peak from here to here. Now, all of us have studied electric machines, and in electric machines, you remember that this point, which is the peak of the torque, corresponds to a slip, which is known as slip at maximum torque, right? So slip at maximum torque, or I can say the speed at which I get the maximum torque in an induction motor, is a function of rotor resistance. Is a function of rotor resistance. So if I have a larger rotor resistance, then I could shift this peak from here to here. So this curve, which was like this curve would become this. So is an AC servo motor, since I want a characteristic of this type, but an induction motor has a characteristic of this type. So this type could be converted to this type if I shift this peak from here to here. Shifting of this peak from here to here is nothing but increase in rotor resistance, and therefore I can say that an AC servo motor has a larger value of X by R ratio. Remember, not large, it is wrong. It should be a smaller value of X by R. This is, yes, this is this is having a larger value of X by R. This is having a smaller value of X by R. Obviously मुझे एक arrow लगाना चाहिए था. This X by R corresponds to this curve, a large value, and this curve corresponds to a smaller value of X by R. It is a simple mathematics. R is in the denominator, so a large value of R will result into a smaller value of X by R ratio. So I can say that this curve is having a smaller value of X by R ratio, and this curve is having a larger value of X by R ratio. So, in a nutshell, we can conclude, if I summarize an AC servo motor, I can conclude that an AC servo motor is a two-phase AC motor consisting of a reference winding and a control winding. Both the windings are displaced at an angle of 90-degree space angle. They are also to be fed by an electric supply having a time displacement of 90-degree electrical, And we know that this motor has to be controlled from this side, that is the control winding side. Therefore, the actuating signal are to be fed to this winding. What are actuating signal? Actuating signals are going to be obtained either from a potentiometric error detector or from a synchro. So this is the point where you are going to control your synchro or you are going to control your potentiometric error detector. Then coming back to the characteristic curve, I want a motor with a negative torque speed characteristics to have a stable operation. I can have this negative slope torque speed characteristic by shifting this curve from here to here. This could only be achieved by increasing the larger value of resistance. Therefore, this curve is for a larger value of x by r ratio, and this is for a smaller value of x by r ratio. So this is all about an AC servo motor. I hope you enjoyed the lecture, although I am intending to go further to consider to discuss some more components of our control system. Look, yes, this is the one. As I have told you, it is its construction is similar to two-phase induction motor. Out of the two windings placed in quadrature, one of the windings excited by a constant voltage, which is known as the reference winding. The torque developed by the rotor is proportional to the control winding. The rotor of an AC servo motor is built with a higher resistance so that X by R ratio is small. We should remember this slide, which is very important. I have already explained you. Now now there is a next component which I was discussing previously also. What is a potentiometer? Let us say, what is a potentiometer? A potentiometer is basically a variable resistive displacement transducer used as an detector. Now, what is the meaning of variable resistive displacement transducer? It is like this: a constant voltage is applied here. This is a fixed resistance value of value. This resistance is Rp. This is the slider which can be moved. This slider can be moved up or down. The value of the resistance that can be tapped depends upon the position of this slider. So let us say this is the total. I will explain it from this. A pair of potentiometer acts as an error detector. Now, how does it acts as an error detector? Basically, uh, go to a slide. This will be more useful. Look, yes, as you can see, this is a potentiometric error detector. There is a constant DC supply. It is having two sliders. One is this slider, second is this slider. You can see one slider is marked as a reference and other is the actual control variable. So whenever you move this slider on this potentiometer, you tap a resistance which depend upon the length you have gone through this sliding arm. So I can say that the resistance tapped by this slider decides the voltage which is available at this point. So I can say that if this the position of this slider and the position of this slider is same, then you will get a zero voltage difference between this point and this point. Since they are tapping the same amount of resistance, you can apply the voltage divider theorem. From voltage divider theorem, you know that if the resistance tapped on both the side is same, so the difference of the voltage will be zero. So this is an example of a potentiometer which is used for comparing two positions. How it is comparing two positions? It is actually converting the difference of two positions into a voltage. It is converting the difference of two positions into a voltage. Now see, this voltage, this error voltage is actually proportional to the difference of this position. This error voltage is amplified, and then this amplified error voltage, if this was the amplified error voltage, this voltage would be the actuating signal. Now, where we can feed this actuating signal? This actuating signal could be fed. Let us say if I am going to work with an AC servo motor and this is an AC amplifier. Let us say this can be converted. This DC signal could be converted by in any way by an AC signal, or I can say that if this was an AC potentiometer, so this AC amplified error voltage would have been fed to the control winding of our AC servo motor. Okay, let us shift back to our potentiometer where we were, where I was explaining the potentiometer. Now, a pair of potentiometer acts as an error detector. Input is the wiper displacement Xi. Okay. Output is the voltage E0. That means whatever be the position of this wiper, it will decide the value of this voltage. Now, total resistance of this potentiometer is Rp. Let us say this total resistance is Rp. Total length of this potentiometer is, let us say, Xt. So the resistance per unit length will be Rp divided by Xt, right? That is this ohms per meter. Now, resistance for the wiper displacement of Xi unit, what I mean to say is, whatever will be the position of this wiper, that position will decide this length Xi. We have already found the resistance of the potentiometer per unit length. So what the resistance of the potentiometer per unit length multiplied by certain length will give you the resistance tapped. So you see there is a, in this case also, if I am tapping a length of Xi meter and if the resistance of the potentiometer is Rp by Xt ohms per meter, so Rp by Xt multiplied by Xi will give me the resistance which has been tapped by this length. Okay. So now we can apply the voltage divider theorem. Now voltage divider theorem says what? Voltage divider theorem says that the output voltage is equal to, the output voltage will be equal to the in V, the total voltage multiplied by the resistance tap divided by the total resistance. So EI multiplied by RP into XTXI divided by RP. Now we can cancel RP and RP. So E output will be equal to Xi by Xt into EI. So it says that the output voltage across the potentiometer is equal to input voltage multiplied by the ratio of the Xi, that is the length, the resistance tapped by the wiper, divided by the total resistance of the wiper. Now, what is a potentiometer? Our potentiometer is meant to achieve the only task that it should convert a position into a voltage. It should convert a position into a voltage, right? So, if I see this equation, if I see this equation, it says that, let us say this equation, E output voltage was equal to Xi by Xt into EI. Okay. Now, let us say that our potentiometer is having a gain. Now, what is the gain of any component? The gain of any component is the ratio of its output with respect to input, right? So, what is the output? What is the output of this potentiometer? It is volt. What is the input of the potentiometer? It was a position xi. So, basically, gain should be the ratio of E0 divided by xi. So E0 divided by xi will be equal to EI by xt. It should be equal to EI by xt. Or I can say that E0 by xi is equal to EI by xt. Okay. Or E0 will be equal to some constant Kp into xi. So this constant Kp will be nothing but Ei by xt. So I can say that the gain of the potentiometer is Ei by xt, right? So it is having a unit of volts per millimeter or volts per meter. Let's forget about the mathematics. The only thing which has to be remembered in a potentiometer is that it takes the input as a position, it gives the output in the form of a voltage, and it has certain gain. That certain gain depends upon the value of its total resistance and the input voltage which has been fed to the potentiometer. Correct. So now, till now, students, we have studied an armature controlled DC servo motor. We have studied a field controlled DC servo motor. We have also seen a potentiometer or a potentiometric error detector. In my next class, I will discuss about synchro. After discussing this synchro, we will discuss a real system like this one, where it will be used to, let us say, control of a position, or we will discuss another system where it will be used for a speed control system. Then we will proceed further, we will go further, and we will develop the mathematical, with the help of mathematical modeling, we will develop the block diagram of the system, then we will simplify the system. So I hope, going sequentially, you could have understood that if I want to analyze any closed loop control system, first of all, I must have a clear cut idea of what components I am going to use. Those components which I am going to use will be governed by which equations. Is I able am I able to mathematically model each component? If I am able to mathematically model each component, then I could be able to develop its block diagram in this way. And if I am going to develop the block diagram in this way, then I could find the transfer function of this system. So I hope you understood the importance of mathematical modeling, and I hope you may have understood how a DC servo motor works, how an AC servo motor works, what is a potentiometer. Quickly, in the next class, I will explain you about a synchro error detector, and then we'll go further on real systems. So, thank you very much and enjoy your vacation.